Thank you very much, Martin. That was a treat. I'm sure none of you have ever heard someone in one talk cover everything from the geology of Mars and the Moon to the topography of the multiverse. So that obviously opens the floor up to a large possibility for debate, which we'll get to. We appreciate Martin for this magisterial presentation. My name's Chris Impey. I'm a professor of astronomy at the University of Arizona. I think Gresham College had been around for about 300 years when my university, a newbie university, was founded. But I do have the pleasure in this coming spring in April of being a visitor here and giving a talk in the Gresham Visiting Professor series. But you're in for a treat tonight because in addition to what you've just heard and the follow-up questions from it, there's a great assemblage of talent from previous professors, Gresham professors, and I'm going to ask them to come up on stage now, and I'll describe how we're going to proceed for the next 45 minutes. So as they take their places, I'll give them in their order, of course, of being Gresham professors. Martin Rees was first appointed as a Gresham professor. We've got Michael Rowan Robinson, Andrew Fabian, Ian Morrison, and Carolyn Crawford. And between them, and you've already heard Martin talking about essentially everything in the universe, between them, everything is on the table. So I'm going to ask each of them to make a few minutes of comments where you'll get their perspective and a sense of their expertise. And then we'll take questions which can be directed to any one of them, or not to anyone in particular, and we'll just see who picks up the question. So let me just start by asking them. We'll just start with Michael.
Hi. Well, I'm Michael Rowan Robinson. So my main interests are infrared astronomy and cosmology, the subject of the last part of Martin's talk. It's interesting that in different wave bands we see completely different pictures of the universe. So in the infrared, what we especially see is dust. So these are little particles of dust which spread through interstellar space, through the solar system. In the solar system we have the zodiacal dust cloud. And that dust is where most of these heavy elements that Martin talked about reside. So our body, the stuff of our bodies has probably spent quite a lot of time sitting in small grains of interstellar dust made of carbon and nitrogen, carbon and oxygen and other key elements. So with infrared astronomy, for example, in the solar system, what we're especially interested in is the solar system's debris disk. So Martin talked about the planets, but the planets are only a tiny part of the solar system. There are hundreds of billions of objects a kilometer in size or bigger, and the zodiacal dust is the debris from these. It flows in towards the sun. Martin showed in his first talk, we saw the Milky Way with these dark patches, which are the clouds where new stars are forming. And in infrared, we see very distant galaxies undergoing huge bursts of star formation. So those are the kind of things that we study in infrared astronomy. And on cosmology, I just say one thing. I think that, as Martin says, these new missions have given us a very detailed picture of the geometry of the universe and quite a lot of information about what it's made of. So ordinary matter, the stuff we're made of, is not very important. Dark matter is much more important. And there's also dark energy, whatever that may be, which governs the current motion of the universe. And this points back towards the inflationary picture at the beginning of the universe that Martin talked about. But personally, I'm very skeptical about the multiverse and all that stuff. I think it's totally speculative. There's no evidence for it. So
I agree.
Okay, well, that's all I wanted to say. Thank you.
And maybe one day.
Ian.
Hello, I'm Ian Morrison. I've in fact been a radio astronomer for virtually 50 years now at the Jodrell Bank Observatory. I have many interests, one of which, of course, is the search for life out there. And for 6 years, I was involved in Project Phoenix, which to date has been the most sophisticated search for ET yet. Obviously, we never found it, otherwise you'd know about it and I'd be quite famous. Neither of those is true. But in fact, radio astronomers have actually made quite a contribution to astronomy in the last 20 years. You've heard some of them, such as the discovery of the cosmic micro background. I'm very pleased that our observatory helped build some of the receiver systems for the Planck spacecraft, and my colleagues are working on the data, and I've been in that for quite a long time. And I do love cosmology as well. It's funny enough, the things I like most, like Einstein and cosmology, I'm an experimental physicist or astronomer. I'm not a theoretician, but I do enjoy them. In the little bit of blurb about the very last lecture I gave as Gresham Professor, I said, or perhaps we live in a multiverse that stretches beyond our imagination. And I was trying to imply that maybe the totality of the cosmos was beyond the ability of our human minds to comprehend. I was actually quite pleased that the following summer, I think in an interview in the Sunday Times, Lord Rees said much the same thing. I sincerely hope I'm wrong. Maybe we will find out. Will we find other life? I worry that there's a problem in getting from single-celled to multi-celled organisms, and then a planet has got to be relatively stable in time, over a long period of time, to allow that to evolve for us. Sadly, I suspect that that will not happen very often, but I sincerely hope it does. Thank you.
Carolyn.
Thank you. So some of you will know I'm the most recent Gresham Professor of Astronomy, and most of my research career has been spent studying some of the largest structures in the universe. I've worked on enormous clusters of galaxies, systems where you've got hundreds, thousands of galaxies all contained in a cluster, maybe sort of a few tens of millions of light years across. And in particular, looking at that central cluster galaxy, and those are the most massive, the most extreme galaxies anywhere in the universe. And of course, the most massive galaxies contain the biggest black holes. So I was an observer using optical, infrared, and X-rays to study the symbiosis of that giant galaxy with its surrounding cluster. But I must confess, over the last 10 years or so, I have moved away from being the person doing the research and discovered an enthusiasm and a passion for communicating the science and the research. And so now, along with my sort of college lecturing, I have a role as a public astronomer in the Institute of Astronomy at Cambridge, where I can indulge my passion for explaining about science. And the best thing for me about what I do now is that it allows me to engage with a much wider breadth of astronomy than just that narrow thing that I was researching. It means I can now indulge my passion for the subject, whether it's just observing the night sky, talking about exoplanets or the latest missions around the solar system, or indeed reverting to talking about clusters of galaxies and some of that large-scale structures. So really, I love all of astronomy, and I love talking about all of astronomy.
Andy.
Yes, I'm Andy Fabian. I was a Gresham Professor back in the early 80s when actually we started having our meetings in the Barbican, and I would give lectures in a cinema, which was a unique experience for me. Back at that time as well, Martin was the director of the Institute of Astronomy where Carolyn and I work, and so he was my boss. I'm now the director of the Institute of Astronomy, so in some sense Martin is, I'm the boss of Martin, although I wouldn't dare tell him what to do. But it certainly is a great privilege having Martin down the corridor to go and sort of gossip to and find out what's really going on. My work is to look at X-rays from the cosmos, and I study things like accreting black holes, trying to look at and understand how material acts under these very extreme conditions. I'm interested in the whole breadth of astronomy, and I like looking at the night sky myself, and I think that there are many, many questions yet to be sorted out. In a way, it sounds a little from Martin's talk as though, you know, we understand everything apart from maybe if we could just put quantum mechanics and gravity together, then everything will be fixed. I suspect in 100 years' time, there will be many new issues which we haven't dreamt of today. I'm very optimistic about the future.
Great. So you have a treat, because never before has this assemblage of erudition on the stage, 5 Gresham professors. I think we invited Sir Christopher Wren. He seems to be a no-show. And basically, we're going to have the floor open. I will just make two framing requests as you ask questions. There are two roving microphones. One, try and frame your question in a compact form so that we can get the most questions in. And second, if you are directing it to a particular person, just say that up front. Also, I think I will follow Martin's lead here and say that if there are any questions about UFOs, I'll start to direct those questions to each other and not to the stage. So the floor is open. Yes. Wait for the microphone, and we'll be passing, because there's no central aisle. It may take a minute to pass the microphone along, so we'll wait for that too. Okay, go ahead.
It's really a double question, if I'm allowed that. The first is, I've never really understood why the further away you look at objects, the objects you look at are, the faster they're receding. If they're expanding, if the universe is expanding at a constant rate, shouldn't they all be moving away at the same rate, whether they're nearby or further away? So that's my first question. It's probably a very stupid question. And the second one is that my understanding was that the expansion of the universe started accelerating at some point in the universe's history. And again, I don't understand why that should be what changed that caused it to start expanding at a higher rate.
We've asked an easy one and a hard one. I'm sure Martin can handle both.
Should I stand up? Can you hear me now? Yes. I think the first question, if you think back to my infinite lattice, okay, then imagine all the rods get longer, then the more distant ones are separated from us by more rods, and so the speed of their apparent recession is proportional to the number of intervening rods. So the whole network is growing, and the further away they are, the faster they are. Now, it is true, as you said, that the expansion rate is now speeding up. And this was discovered in 1998 and is indeed one of the big surprises. It seems that the universe in the early stages was expanding but slowing down, as you would expect, because everything exerts a gravitational pull on everything else. So you'd expect that there would be a gradual decelerating pull. But it seems, and this was a big surprise, that there's some extra force latent in empty space, which, when the density of matter becomes low enough, starts to dominate. And so the push, due to empty space itself, overwhelms the gravity which the galaxies exert on each other, and we get an acceleration. And there are theories which model this, but the fact that this repulsive force existed was something which was a big surprise. And it's something which I think we won't understand until we understand the nature of empty space in a fundamental way. Everyone suspects that if we are to unify the very large and the very small, as in my snake eating its tail, we will have to consider phenomena on a scale which is 1 billion times smaller than an atomic nucleus. That's the scale where quantum effects and gravity open up. And most people suspect that if you were to chop up space, then you couldn't do it indefinitely. We know I can't chop up this lepton until we get down to atoms, then it stops. But most people suspect that if you try to chop up space, when you get down to that very tiny scale, you will find that what looks like a point in our space is actually a tightly wound origami in extra dimensions. This is what string theorists are talking about. And until we understand a theory like that, we won't understand why this mysterious force exists. It's one of the deepest mysteries, and it may be something we'll never understand, but we're trying.
I'm thinking if Michael thinks multiverse is speculative, you probably also raise your eyebrows there too.
Well, I don't disagree with Martin that we're not likely to find an explanation for the acceleration of the universe unless we understand better the connection between quantum theory and general relativity. But I think one of the questions that you asked was, why did the Big Bang get started? And I think that is an interesting question, but I think it's an example of a question that we just cannot answer, because we have no evidence from the moment of the Big Bang. We have it from the from our telescopes, we see very distant galaxies, maybe a billion years after the Big Bang. From the microwave background, as Martin said, we go back to a few 100,000 years after the Big Bang. From other evidence, like the manufacture of helium during the Big Bang, we get back to 1 second. Now, we just cannot get back so far near to this moment of the Big Bang. So we don't know what its structure is or why it got started. People speculate about it. I mean, there's a lovely one idea that floats around is that the universe existed for an infinite time in a kind of shadowy quantum vacuum, and then there was some unusual fluctuation which led to this expanding universe growing out of a fluctuation. So you can think that it might be that time didn't start at the Big Bang, that there was a time before that with this shadowy quantum world. But that's just speculation. We don't have any evidence back to that point. And so we just cannot really begin to answer that question. Theorists like to have a go at it, but without evidence, I don't see how we can make much progress. So there are certain questions we have to set aside because we just don't have any evidence that will help us answer them.
Yes, in the front here.
In the increasing complexity of the subject, I can see no beginning or end to this increasing complexity, even long after the Earth has been gobbled up by the sun running out of fuel. The question that I would ask is, what alternative would you have in a religion to call a focal point a God, Allah, or whatever, because of this complexity, this ever-increasing unknown? Leave it at that point.
Well,
okay, who wants to take
I
that?
disagree that I disagree that the unknown is increasing. On the contrary, that what Martin portrayed in the history of science, and especially of astronomy, is that all the time things had appeared very mysterious, like the motion of the planets to start with, and then in our own century, the universe and its history. I mean, when Martin and I started research, I mean, we knew nothing really about the universe and what its structure was and how. I mean, we knew about the expansion of the universe. That was about all. So basically, as time goes on, as we study things about which we have some evidence, and that's the problem with the Big Bang itself, we don't have evidence about that. But where we have evidence, we can make progress and reduce this area of uncertainty. So I just don't agree that anything about the universe tells us that we need God to explain it. I mean, there are some things we haven't explained. There are some things we don't understand. There's a lot of detail, for example, in how stars form, how galaxies form, how planets form. We haven't got it all sorted by any means. But I think we will understand them by studying them, by building new telescopes and space missions, and so on. I don't see the need for God.
If I might be allowed to recast the question, because something Martin has written and spoken about is the situation of a very simple, unified beginning of the universe, and then a large old universe that has a lot of complexity, including the complexity of all of us in this room talking about the subject. And you've addressed some of these issues, the nature of the universe in terms of complexity or entropy. Is there any comment you'd make on that?
Well, I'd like to say just two things. First, that the most complicated things are living things. They're more complicated than anything in the universe, which is inanimate, in my opinion. And to follow up what Michael said, many of the issues which were controversial 50 years ago when we were students have now been settled. And the questions we are tackling now couldn't even have been posed back then. And that's the nature in which science is a progressive enterprise, whereas trying to address questions which have been posed by the fact that observations are much more precise. And I think it's important for us to emphasize that armchair theory doesn't get you very far in this subject. We're no wiser than Aristotle was. And it's 95% due to new equipment and better computers that we have made these advances. We just try to make sense of it.
Ian.
You talked about a God. In his talk, Sir Martin mentioned the Anthropic principle, why are we here? There's a wonderful book that he wrote some years ago called Just Six Numbers, which makes the point that if some of the parameters that define our universe were not as they were, we could not be here. So then there's a question of why is it right? Well, one possibility, and I don't think you can discount it, is that a single God created, or a God, whatever you think that is, created a universe fit for life. I quite like that in a way, because if you were a wonderful musician, composer, artist, what is the point of making a wonderful piece of art if no one can see it? So perhaps if you were going to make a universe, you'd definitely make it so that life like ours could arise to appreciate, as you've seen this evening, the wonders of that universe. Now, the alternative, of course, is something that I don't seem to like down here, but there's a multiverse, at least some of them, where there are myriads of universes, all which have perhaps different properties, and so some of them, by chance, will be right for life. And you can perhaps ask, well, where are they? I don't think we'll ever know. But there's a bit of an analogy. It's based on the idea of string theory, that basically there were a lot of string theories where there were 10 dimensions. 6 of them were curled up to form the little strings that form the particles you've heard a bit about. But Ed Witten, a wonderful physicist, combined them all into what he called M theory, where there were 11 dimensions, a further 5th dimension. And perhaps these universes all live in that 5th dimension without knowing about each other. And finally, a little analogy of that, if you had a knitting needle and 3 slices of bread with some ants on the right side of each of those slices, to some sense, they're defined to be in a 2-dimensional universe. They can only move sort of up, down, sideways. And they certainly wouldn't know about the other ants on the other sheet, a piece of bread. So in perhaps the same way, we in our 3rd dimension know about our own universe, but there's no way we conceive about the presence of others that might exist in a further dimension.
Yes, at the back there. Just wait a minute. We'll get the mic to you.
Oh, I know this guy.
In support of what Ian's just said, his predecessor was a great advocate of multiverses, John Barrow, and his lectures used to contain an awful lot of information and suggestions about that. But my question is, the Large Hadron Collider hasn't been mentioned this evening, and it's in its 2nd phase, as I understand it, and they have discovered some negative subatomic particles. But how much evidence is there that that will compute to a quantity of dark matter sufficient to justify current percentages of the universe?
Of course, the LHC discovered the Higgs particle, and that was the last piece of the jigsaw which gave people confidence that their picture of existing particles was on the right lines. But of course, the hope is that it may discover some other particles. In particular, there are speculations about a class of so-called supersymmetric particles which don't exist in the everyday world, but could have been made in the early universe and could make the dark matter. And so there's a hope that the LHC may be able to create some of these particles by reproducing conditions that haven't existed since the first nanosecond of the Big Bang. So that would be great if that happens, but don't hold your breath. It could be that it won't detect these and that the dark matter particles may be much, much heavier than anything that the LHC could produce. So we hope the LHC will produce something, but we can't be sure.
I'll just add to that. Even if we're successful, and we should know perhaps within the next couple of years about whether we can identify a potential dark matter candidate from the LHC, that's only part of the battle. That might illuminate some of the physics. It might give us a candidate for the dark matter. You then have to prove that it exists in enough quantities in the right places in the universe to account for the astronomical observations. And not only that, that it will be stable and long-lived enough to have survived since the Big Bang to hang around and litter up our current universe. So you've got to have the work from the LHC, but it's also got to be backed up with the astronomical observations. So there's quite a lot of development yet to go in this field.
I can't resist asking, since Martin gets the UFO questions he alluded to. Andy, do you get the questions about LHC making black holes, devouring them?
Well, yes. Fortunately, it's very unlikely that the LHC will make black holes unless there are other dimensions. And that's, we've already heard mention about other dimensions. And there is an idea that gravity is so weak. Martin told us that it's 40 powers of 10 weaker than, say, electric fields and so forth. The reason that gravity is so weak is because it's leaked away into another dimension. And if you can penetrate to that other dimension by slinging protons fast enough at each other, they can suddenly, their gravity becomes extremely strong and they turn into black holes and so forth. So that would be really exciting. I think there's already been a book written about it, but a fictional book, but of course, but it very exciting. But I think it's highly unlikely that's going to happen. Other dimensions are something that we all think about occasionally, but for which there is currently zero observational evidence. And I'm an astronomer who likes to see something and then I'll start believing it, rather than so much as it's great to speculate, but it's really good to see the observations.
If you're worried about whether the LHC is going to destroy mankind and the world, there's a website, www.hasthelhcdestroyedtheearth.com. I went on it the other day to check and it said no.
Okay. Let's have another question. Yes, up there on the right in the blue tie.
Lord Rees mentioned that the future evolution of man might make us something quite different than what we are right now. And the question has been raised, what caused the Big Bang, or what we refer to as creation? I'd be curious to know if anyone in the panel has considered any of the thinking of Teilhard de Chardin, who wrote about creation and the future of Homo sapiens, and if so, did they have any comments?
That's open to anyone.
Well, 2 points. I mean, I must say I'm not a great fan of Teilhard de Chardin, because I remember the wonderful review of his book by Peter Medawar, who's one of my scientific heroes, who was rather skeptical about this. He said that before deceiving others, he's been to great pains to deceive himself. That's what he said about Teilhard. But seriously, he did have the idea that we were advancing towards some sort of common mind, the noosphere. And maybe there's something in that, because if we think of what's going to happen in the future, then even within a century or two, it may well be that human brains will be surpassed by AI, artificial intelligence. And then, of course, if the machines can themselves make something even better, then, of course, we will be getting into a situation where the dominant cogitations will no longer come from the wet hardware in human brains, in human skulls, but will come from machines. And then you can imagine that it will be a sort of network. So if we think of the far future, then indeed it could be that it will be an inorganic future where there will be machines of vastly superhuman powers. And incidentally, going back to the SETI searches, I think if they are going to discover anything, it's far more likely to be something like that than an organic civilization like we have on Earth.
It's Fred Hoyle's Black Cloud.
Yeah.
Yes.
Not so far off.
Yes.
Probably the next but one Gresham Professor of Astronomy will be a bot.
Right,
So
yes.
enjoy the
Yes.
flesh and blood versions while you can.
Yes, okay.
Another question. Yes, right at the back on the right.
Thank you, Lord Rees, for a lovely talk. You mentioned briefly in it dark matter and dark energy. We've just touched a question there on dark matter, but I wonder if the panel could speak a little on the dark energy side. It's something that doesn't get a lot of public understanding, and I wonder if that's because no one knows anything about it, or what. But perhaps if you could give us a sort of a state of play on it, and perhaps any strategies as to how it might be brought forward in knowledge.
Yes. Well, I mean, we know that this force exists. We don't know much about it, except it seems to be fairly uniform. It seems to, as far as we can tell, be equal strength in the past as it is now. And that's all we know. I think we won't understand it better for a very long time. But fortunately, it's not as important as dark matter in helping us to interpret stars and galaxies. It's important in intergalactic space, but whereas dark matter is crucial in determining the way galaxies form and their morphology, etc., the dark energy is irrelevant to that and only affects the overall dynamics of the universe. So although you sometimes see a pie diagram where the dark energy is presented as a dominant contribution, it's not as important as dark matter in terms of helping us to understand what's going on in galaxies and stars.
Michael.
There are two ways of looking at dark energy. One is that it's the energy density of the vacuum. So that's what the phrase dark energy is sort of referring to, the idea that it's the energy of the vacuum, and this has a repulsive effect and causes, on the large scale in the universe, causes this expansion of this acceleration of the expansion. So that's one idea, that it's to do with the vacuum, therefore that there'd probably be some particle connected to it and so on, a quantum explanation. So that's, but there is another way of thinking about it, and that is to say, well, actually, in Einstein's general relativity, instead of just having one constant of gravity, the constant of gravity that's to do with pulling things together, there's another constant of gravity, the cosmological constant, which is about pushing. So on small scale, gravity pulls, on the large scale, gravity pushes. And so in that way of looking at it, it's a kind of macroscopic feature of gravity. It's not to do with the vacuum, it's not a dark energy, it's just the way gravity works on the large scale. And so that could be what we're seeing. But again, to understand it fully, we would have to get into these bigger theories that combined quantum theory and gravity, and then maybe it would start to understand why there are these two constants.
Einstein put in that constant as a fudge factor. He believed at the time, as many astronomers did, that the universe was static, that things just stayed where they were. But of course, gravity is attractive. So if you had a lot of galaxies spread out in space, eventually they just collapsed down into a heap. So he added this cosmological constant to basically balance it out. But later he realized this was a totally unstable situation. If the galaxies got a bit further apart, the anti-gravity would win, they'd fly apart, closer together, things would collapse. So he said this was the worst blunder of his life. But of course, when it was discovered that the universe was expanding, he realized that he could actually have predicted that there would be an expanding or a contracting universe. And now, of course, perhaps we know he wasn't quite so wrong after all.
Okay, well, it's running out of things to add to that, but just to clarify, if there is anyone in the audience who is still confused about this dark matter and this dark energy, because they sound like they ought to be similar things, as these gentlemen have said, you've got to realize that dark matter is associated with gravity. It's associated with stuff. That's why it's crucial, as Martin said, to allow galaxies to congregate, masses to grow in time to see the universe that we see around us. The dark energy, whether it's the repulsive gravitational force on large scales or some other thing associated with the vacuum of space, that is associated with nothing. It's associated with the voids of space. This is why in the early universe, dark matter is so important, because stuff is close together, it's pulling stuff together, gravity wins. But as the expansion of the universe grows, matter becomes more diluted throughout the universe. You've got those voids become bigger, the dark energy goes bigger. And so as it grows stronger, and the universe grows bigger, and those voids grow bigger, dark energy gets stronger, It may not have been important for our past, but this is why it's important for our future. And determining the nature of the dark energy, its relation to that vacuum, the void of space, is really what will determine whether we're going to end up in a big rip or a big chill 20 or however many billion years in the future.
Doesn't leave much for me, but just a simple thing to understand is the word dark to a physicist or an astronomer means we don't understand it.
Simple honesty there at the end of the line. Yes, let's have another question. Sure.
From time to time in the history of physics, there have been statements to the effect that the big questions have been solved and essentially a closed system is close to being formed. Andrew Fabian, in his introduction, gave a sense of the excitement of knowing your ignorance. How much longer is there going to be a supply of inflationary fields of ignorance within physics and astronomy, which will give your great-great-grandchildren the potential for careers in astrophysics?
Yes.
If I can start that one off, basically there's dark energy and dark matter. They're things we don't understand. There are dark photons about which I know even less, and we could carry on. But I have found throughout my career that continually we're finding new things to puzzle about, and new fundamental things. We can ask questions and start to give answers to things that we couldn't think of decades ago. I am very optimistic that we haven't come to the end, that the physics books that we've got today will be looked on in 100 years' time or 200 years' time as being, gosh, did they really believe that kind of thing? And I remind you that, late Victorian times, people really believed in the ether, and then it was discovered that it doesn't exist. And we are likely to have other theories keep rolling on. So I think it's mainly that I see many things around that are really intriguing. We're looking, we've got more and more telescopes and more things we can observe, and there's just so much more to look at.
I'd like to hear from all the panelists on this. Let me add a layer, though, about the possibility that some of the questions are too hard to answer. Is there some anthropocentric hubris that we enjoy at this time to imagine that we can answer all these big questions still on the table?
Good point.
Well, I would just like to remind everyone of that quote for which he was ridiculed. I believe it was Donald Rumsfeld who... My turn to go first, yeah. Just that quote where he mentions about the unknown unknowns, and he was ridiculed for this, whereas I would say I and so many other scientists rely and positively look forward to discovering those unknown unknowns. If they weren't there, we'd give up now. Okay, it's really exciting to think there's so much left to be discovered, so much left to understand, and it's that drives so many scientists, whether they're going to be my great, however many grandchildren. I really think it's exciting, and we absolutely need that sense of unknown.
Absolutely. The big new thing in radio astronomy is going to be the square kilometre array, based the headquarters, in fact, at Jodrell Bank. But the point is, there are a number of things that it's aimed to do. We can look at pulsars, all these various things. But one of them is to discover things that we have no idea exists. And almost every major new instrument that's ever been built in the world, that's perhaps had a factor of 10 advancement in its capabilities, has actually discovered things that were not known about before it was built. Let us just hope that continues to happen in the future. There will be lots for our research students and their research students and so on in the future.
I'm going to express a concern, and that is that we've reached a point where, in astronomy, where the telescopes we're building are at the limit of what can be built with every advanced nation contributing together. It's like the Square Kilometre Array, the ALMA project in submillimetre, and we have the European Extremely Large Telescope with 40-metre dish. I mean, and similarly with the space missions, that basically we're making things as big as we can at the moment, and to make anything 10 times bigger it's going to be extraordinarily difficult. And so we may be coming towards the end of a period, which we've been very lucky to live through, in which every wave band was opened up with new space missions or instruments, and wonderful discoveries were made quite cheaply, really, at the beginning. And then gradually we got to the point in each field where the missions and the telescopes are gigantic. They have to be international on an immense scale. And so I cannot see that can continue at the same rate of growth for the next century. I mean, I think we'll have to be very selective about the questions we try to address. The Large Hadron Collider is another example. I mean, it's a vast international machine. You really have to think, how are they going to make a bigger machine than that? It's practically at the limit of what we can put together. Unless you're willing to spend 30% of your income on science. I mean, currently I think you spend about 0.5% or something is what governments and so on spend on your behalf on science. But if you're willing to say, okay, we'll give up football, and we'll give up all sorts of expensive pleasures and funnel it all into the next big telescope, well, then maybe we can have some bigger telescopes. But it isn't going to be quite the same as it's been for the past 50 years, I think.
It's an excellent question, and I'm going to let Martin have the last word on this and for the panel discussion. We'll find out whether he's an optimist or a pessimist.
Is this the real last word? Well, first, I wish Rumsfeld had stuck to philosophy. But I'm not quite as pessimistic as Michael. It's true that any particular subfield does eventually get to this gigantism, etc. But new fields start up. And for instance, planets around other stars. Is there life on them? This field didn't exist 20 years ago. A lot can be done with small telescopes. Ideas of the origin of life can be done by individuals with clever ideas. So I think there'll be new subjects starting up where we can work without great resources. And I certainly hope so. As science advances, the periphery gets longer and the frontier with the unknown therefore gets more extensive. And I think planets around other stars and life on those planets is going to be a very important subject in this century, as well as the more fundamental physics areas. There is the question which was alluded to about whether there will be some things which we will never understand because our brains aren't up to it. And I think we must be open-minded about that, because just as we know a monkey can't understand quantum theory, there may be some fundamental features of reality which are just beyond the powers of human brains to grasp. We've got to be open-minded about that. But I think there are many that we can grasp, and just as there's been huge progress in the last 50 years, there'll be more in the next 50 years. And finally, since the multiverse came up, I'd like to end with an anecdote, a conference where I was on a panel and we were asked about how much would we bet on the multiverse. And I said, well, on a scale, would you bet your goldfish or your dog or your life? I was nearly at the dog level. And the other person on the panel was Andre Linde. He's the inventor of the eternal inflation idea. And he spent 25 years working on it. He said he would bet his life on the idea. And then at a later meeting, the great theorist Steven Weinberg said, when he was asked a question, he'd happily bet Martin Rees's dog and Andre Linde's life.
Okay, that's great. Well, thanks for your excellent questions. You are, in a minute, going to be invited to Edward Lumley Hall, which is outside and on the left for a reception. But first, please thank Lord Rees and the excellent panelists for a wonderful evening.